Okay, so hopefully you've gotten started on this project because your last chance to get help is tomorrow because it's due Monday and office hours are all day tomorrow. So highly suggest, I would guess that most of you are going to need some guidance, some assistance, some support on this. And so make sure that you get in tomorrow to office hours if you need help to work on this project. Okay? Let's make sure we understand the situation, right? So Clara is on a leash, right? She's tethered to a leash that's attached to the silo at the westernmost point. So the blue is the leash. The blue right now it's a line. And then the main goal of this is to find this boundary for which she could graze. So if she were to walk out away, so the leash wraps exactly halfway around, and if she were to walk and peel it off, keeping it always tight, what would that parametric curve be? That's kind of the big question. How would we define that parametric curve that I'm showing in pink here? So before we do any digging into finding equations and variables and solving things, we really got to understand the situation. So any questions for clarification questions on understanding the situation, which is always should be your first thing that you do when you come to a problem like this. Okay, nice and loud. No, it could. That's how I did the animation. So yeah, so the cow, and in fact, I think there's one question about it going down. So at this point, the cow could keep walking and then wrap it around the bottom side of the silo too, the south side. And then it would get back to the east side if it wrapped it underneath. So it's just the way that I have the animation set up, that I have it stop at the westernmost point and wrap back. But it could keep going and basically is all symmetric about the x-axis. So that it would come back down around and wrap around the bottom of the silo. And it would just, again, reach to the easternmost point. So that's the realistic situation. So keep going, wrap around.
So would the area of the bottom plus the top just be the area of the top minus 3?
So yeah, so he's asking, is the total area that the cow could graze in, the area above the x-axis times 2? Is the total area that the cow could graze in the area that the cow could graze in above the x-axis times 2? Hopefully that's an easy question. I'll leave it to you to decide. Does it make sense? Yes? Just do each question in succession. Do each question in succession. It will guide you through, and then you'll discover the answer to your question. But don't try to press on to questions if you haven't fully gotten this 100% correct answer on the current question. So it may take a little discipline, and instead avoid the temptation to go forward. Work on the one you're working on until you get that right, and you know it's right, and then move on to the next. Okay? Other questions about the project or understanding the situation? Okay, due Monday, so get started on it if you're going to need some help tomorrow in office hours, okay? And then I'm videoing now, so if you want to watch this again to help you, you can watch the beginning of today's class video. Okay, let's go ahead and do the last one, since that had the lowest success. So they want the area 57ths. Okay, they want the area bounded by this parametric curve and y equals 57ths. Okay, this parametric curve in 57ths. So we need a good picture of this. It's a little bit. Okay, so it's kind of like a parabola, but it's more V-ish. Okay, that's what this turns out to be, something like that. And then y equals, my problem says 57ths. Yours might have been slightly different. And then this is our parametric equation. And so the area enclosed by those two would be this right here. And so if you remember back from early in the course, to get the area, we're going to think of typical strips, right? Typical strips. And those typical strips, we want the area of a typical strip, which would be a base times height. And what would the base be? The base would be a little change in x, and the height would be the difference in y's. So we did stuff like that. But I think it was early February, maybe. February we worked on this. And so you got that typical strip is a rectangle, and the height of it is y2, or the top value of y minus the bottom, and then the width would be delta x. And then we would, back when we were just dealing with y as a function of x, then we would just basically set up this integral like this. And it'd be from x left to x right. If this is x left here, and x right. But we have these parametric equations, and it very possibly could be that it's difficult or complicated to write y as a function of x. But as parametric equations, it's a fairly simple function. It's a fairly simple function, and so oftentimes then we want to stick with the parametric equations to keep things easy, right? So we saw examples where if you tried to write y as a function of x, it would either be really complicated or impossible. And so we saw the advantage in situations like these to a parametric. So we're going to do this exact same thing. It's the same approach, but we're going to be applying or doing this whole thing in terms of t, using the parametric equations. And so what is y2? So we're just going to change this whole integral into parametric equations. This is what I need to do. That's what I need to do. Okay, that's better. All right. So what is y2 in this situation? Well, that's the higher y, right? So we're taking like the higher y minus the lower y to get that change in y. And so that y2 is just 57ths. And what is y1? Well, it's the y coordinate of this point right here. And what is that? Well, that's according to our, in terms of t, that's according to our y parametric equation. So it's going to be t plus 1 over t. So there's the y2 minus y1. Okay, what is dx? So we did this last time. So if x is t minus 1 over t, then dx is? So if we call this some function of t, then dx is f prime of t dt. And so in this case it is f prime of t, which is 1 minus or plus t to the minus 2 So derivative of t to the minus 1 would be negative t to the minus 2, with the negative makes plus dt. So there's the integrand. This is our y2 minus y1, and this whole thing is dx. So all that's left is our limits of integration. So what will our limits of integration is going to be? We were talking about which typical strips do we need to add up to get this area? Which ones? So all of them starting from here, all the way across until here. So this is our starting point of the region, and this is our ending point. But we're writing that integral in terms of t. So what will we have for our limits of integration? X left and x right? No, we want the t. We want t for the left point. T left. And t right. So why? Because we're differentiating with respect to t. We've got this whole thing in terms of t. Now it's preserving the meaning of width x and height y and adding up all those rectangles in x and y. It's just we're rewriting that sum of those rectangles in terms of t. Okay, so how are we going to get t left and t right? Well, what's true about those points? Those points is where this curve has a y value of 57ths, right? We want to know where does this curve here have a y value of 57ths? Well, that curve is here, so we're going to say 57ths equals t plus 1 over t. And somehow we got to get these t values that make this true. So you could use a graphical solution to this, or if you want to do algebraically, we could get a quadratic by multiplying the whole thing by t, so we'd have t squared minus 50 over 7t plus 1 equals 0. If I multiply everything by t and move everything to one side, and then I can multiply by 7 and hope that this factors. So we'd have 7t does it factor? Looks like minus 7 and minus 1. But minus 7 here to get minus 49. Minus 1 is minus 50. So we get t as a 7th. And so this problem was very rigged. It's very rigged. Just like all real-world problems in the real world are. They're all rigged like that. No, not. But so that's one problem with a lot of problems that are written. Is they give you this impression that everything turns out nice, right? But if we're applying mathematics truly applying mathematics to the real world, we often don't have things work out nicely like this. Okay, but it did. So we'll just make note of that. And then so t is 1/7. That's going to be actually it ends up being t left. We could verify that by putting into x. When t is 1/7, x is negative, indicating that it's this point over here. When t is 7, x is positive, indicating this point over here. So we're going to integrate from t equals 1/7 to 7. How do we do that integral? We just have two polynomials here. Well, very close to polynomials. These aren't quite polynomials, but they're like polynomials, just with a couple negative exponents. We're going to multiply that out, and we end up with 4 or 6 terms or something. And then we got an easy antiderivative, okay? And that will equal that area, the enclosed region. Okay, questions on that problem? Any questions? So again, we're following this. We're still following it the way we used to do. Vertical, in this case, vertical strips with a width of x, delta x, and a height of a change in y. And we're going to sum all those up from left to right. We're going to add up all those really thin rectangles from left to right. It's just we're rewriting that expression in terms of t. We're not taking a new approach. We just have a different way of expressing that function, and then we're going to write that integral with a different variable t instead of writing it in terms of x. But the approach is the same. Okay, any questions on that? Okay, so now I want to use the same problem to talk about something new. I want to talk about curve length in parametric functions. So we'll go back, we'll use the same. Say we want the length of the curve from those two intersection points. So this was t equals 1/7 and t equals 7. And so we're interested in what's the length of the curve? What's the length of that curve from there to there? So again, it's gonna be the exact same approach as before, but we just need to adjust it for the fact that we're dealing with a parametric function in terms of t. And so what did we do before? We looked at I'll exaggerate it here. We started with line segments. And we said if we added up a bunch of little line segments between points on that curve, and then let those points get really close together and make those segments smaller and smaller, and added up all the lengths of those little segments, we would, for very small segments, we would get a value indistinguishable from the actual length of the curve. So how did we do that? So how did we get the length? We call this delta S. So like if we had a bunch of them and like the ith one, how did we find delta Si? Remember how we did that? The what? No, but that's what we're deriving. We're deriving an arc length formula. So how did we? So we started with a little tiny line segment. How do we find the length of that line segment? Okay, and the distance formula comes from? Yeah, Pythagorean, right? So for every little line segment, there's an associated what? Change in x and change in y. So imagine we have a bunch of these, right? We have a bunch of these little line segments from one point to another, and we're numbering them, the first, the second, the third. So this is just a generic, the ith one, right? And so what is delta Si? How do we calculate that?
Delta xi squared
Delta xi squared plus delta yi squared. Is that right? Is that delta Si? One more thing? Yeah, if that would be delta Si squared, right? So if we wanted delta Si, then it'd be the square root of that whole thing. So that's the length of this one little segment. Again, just using x and y. And what do I want to do? I want to sum all those up. I equals 1 to, like say, n of them. And so thinking about what happened before, and we anticipate that we know we want this to be derivatives, right? We want to eventually, these are going to be derivatives. Okay, so derivatives with respect to what? So this is the total length is approximately the sum of all the little segments, right? And so what does that equal? So since we're doing it now in terms of t, we're anticipating that we're going to involve the derivatives of x and y with respect to t. These are all subscript I. squared, right? But I can't just divide. I can't just divide by delta t squared in the denominator. I've got to, if I want to keep things equal, how can I keep things equal? So what do I have here? I have delta t squared inside the radical in the denominator. So that's what I really just did, is I just really divided by delta t, right? Because if it's delta t squared in the denominator, but the square root of it, what I've really done is I've really just divided that whole thing by delta t. So to make it equal to what I had before, I would have to multiply by delta t. So I multiply by delta t on the outside, and I also divide by delta t, and I put it under the radical, which means it'd be delta t squared under the radical in the denominator. So now this expression is equal to, the sum, is equal to what I had before. So this whole thing is equal to this whole thing. I just basically multiplied and divided by delta ti. So it preserves the value. But then that dividing by delta ti was as squared under the square root. Okay, and then we're going to let things get small. And we get the exact length. So now let delta t get small so that we have a zillion little tiny straight line segments connecting very close points on the curve, so that when we add up all those line segments, we get a value indistinguishable from the length of the curve. And when we do that, this sum becomes what? Integral, right? So of radical dx dt squared plus dy dt squared dt. And then from t1 to t2. So there's our, this is dt here. This is dy. Okay, so here's our arc length formula for if you've got your curve represented in parametric form. All right, so go ahead and set up the integral. Can you set up the integral for the length of the curve from those intersection points that we talked about before? So set up an integral for length of the curve from here. This was t equals 1/7. And this was t equals 7. Here's the curve. Just do the first step. Just set up the integral that would calculate the length of the curve from there to there. Is it t, the first one t minus 1 over t? Is that right? And t plus 1 over t? Do you remember, is that the right function? Anyone remember? What was it? How many sevenths? 57. Thank you. Okay, we're gonna. I'll write down the. Don't do any math on this. We'll just set it up, get it set up correctly, everything filled in, and then we'll have the calculator do it. But let's make a prediction as to what that curve length is going to be. So this is the point, 0, 2, and this is what? This is -7, right? X equals -7. And y, it's about 7. So approximately 7. And then this is 7 and approximately 7. All right, so you guys do some rough estimation calculations to predict. Can you predict what the length of the curve would be from that intersection point to that intersection point, or the value of the integral that you should have just set up? Okay, so can you do some napkin mathematics to make a rough sketch or make a rough estimate of what value this integral is going to calculate? Go. Work together if you want to. Just need to get something to get in the ballpark. Something to get the ballpark. Okay, is this the integral that you got? dx dt squared plus dy dt squared, all square root, and then dt. Is this what you set up? And then we're going to go from 1/7 to 7, and what were some predictions for what we'll get based on something more than 14? 19-ish? 15? So yeah, so you could just find that what would be the length of the straight line. Did you do that? Just use Pythagorean theorem. What would be the length of that straight line from there to there? Times 2. Is that what you did? Go from -7 to 0, 2. Use the Pythagorean theorem. Multiply by 2. How many people did that? Some. And what do you get when you do that? Nice and loud. What do you get? 17.4. Okay, so the length of the curve is 17.4. So it makes sense with what we predicted. Questions on curve length, arc length, in parametric? Okay, so you've got all the tools you need for the Clara project now. So everything you need for the Clara project. Again, get started, get help tomorrow. So we're going to move on to the next topic, which is the last topic of the course, which is polar coordinates and calculus in polar coordinates. So polar coordinates is a way of totally reorganizing how we graph things in the plane. It's a whole new system of finding points and plotting functions. It's a totally different system. What's the system we have now? The system we have now is called Cartesian coordinates, or what we've used up to this point, Cartesian coordinates, where your distance from the y-axis is what? What's the distance from the y-axis in Cartesian coordinates? X. Your x-coordinate is distance from the y-axis, and your y-coordinate is distance from the x-axis. So that's called rectangular coordinates. It's all based on rectangles, right? Moving left and right, moving up and down. Polar coordinates, totally different. What we use is distance from the pole. So now the origin is called the pole. So think of like the North Pole or the South Pole. It's like we're looking down on the top of the world here. And the origin is now called the pole. And so one of the coordinates that we use, rather than using x and y, is distance from the pole, and that's r. Okay? Distance from the pole is r. And then the other coordinate we use is our standard trig angle. So we're going to sweep an angle. First. Yeah, so we're going to sweep an angle counterclockwise from 3 o'clock. And so you're focusing on the black line. So we're going to sweep an angle counterclockwise from 3 o'clock. And then and so that angle, let's do 45. Yeah, okay, so let's go right here. So here's a point, and so the angle is pi over 4. I swept halfway through the first quadrant, angle theta of pi over 4, and distance from the pole of 4, because it's on the circle of radius 4, right? So by noting the angle swept from 3 o'clock and the distance from the pole, those two values together pinpoint that location in the plane rather than x and y. So this is the point 4 comma pi over 4 in polar coordinates. So we'll usually use radians, but you can use any angle measure that you prefer. So this might be something like, what, 175 and 2.5. Now notice, that's not negative 2.5, because when you sweep an angle to 175 degrees, you're pointing in that direction. That becomes the positive direction for distance from the pole, is to the left and a little bit up. So that's not r of negative 2.5, that's r of positive 2.5. So whatever direction your angle points, that's the direction of positive. That could be in any quadrant, right? Whatever direction the angle points, the terminal ray of the angle points, is your direction of positive. So you've got positive in all 4 quadrants. Okay, but then there is negative r. So then, given that direction of positive r, the direction of negative r would be back the other way from the pole. So that's what I'm showing by the red line. So if this is the point 175 degrees and 2.5, this is the point 175 degrees and negative 7. So we're talking about the angle pointing mostly left, a little bit up, 175 degrees. but then in the negative direction for r would be back 180 degrees from that, back this way. So that could be the point 175 degrees, -7. But that same point in the plane then could be expressed. If I came around here, how else could I express that point? It doesn't look like I can get on it. So we'll just pretend that that's going through it. So now what angle would give a positive r of 7? So what angle could I put a positive r value of 7 and get that exact same point? 355, right? 355 and 7 would be the exact same point in the plane as 175 -7. Does it make sense? All right, so we'll practice that, but I want to show you how functions work out then. Okay, so we'll practice more of that. That's just a kind of a warm-up, a basic intro to that. So points are expressed as distance from the pole, r, and angle measure. Swept counterclockwise from 3 o'clock. So polar curves then have the form r is a function of theta. So given a certain theta is determining or predicting what r would be. So let's show a cool example here. So this particular function right here, r equals e to the sine theta minus 2 cosine 4 theta. That's the function I want to show here. So what? The distance from the pole is determined by the value of theta according to that expression right there. So we still have functions, but now it's r as a function of theta. So it's not graphing it. Thought I turned it on. This one. So right now for this angle of theta, we get this value of r, this distance. And so then as theta increases, every value of theta has a resulting value of r that plots a point, and when you plot all the points, you get curves. So that's what you get when r changes from 0 to pi over 2. And then as r changes from pi over 2 to pi, you get that. And then when theta changes from pi to 3 pi over 2, you get. So right now, r is negative, right? So for something like 3 pi over 2, we're getting a negative value of r because the positive direction of the angle is down, but we're plotting a point up here in the other direction on the red line. So right now for around 3 pi over 2, our values are negative. Our values are negative. So this was one theta changing from 0 to 2 pi, and then all the values of r associated with all those values of theta. And that was this function right here, e to the sine theta minus 2 cosine 4 theta. Results in that graph. Okay, so let's practice. Go back to practice. I wanted to show you an example of a function. So here's some practice. We're going to plot each point and find the rectangular coordinates. Oh, so rectangular coordinates. We got to do that. So let's start with let's do pi over 3. What are these in? 24 divided by sixths, right? Right, okay, so this is the angle pi over 3. And say we do the point pi over 3, 2. Let's do, we got 1, 2, and 3, so let's do 4. So this is the point 4 comma pi over 3. How would we express that point 4 comma pi over 3 in rectangular coordinates as an ordered pair x and y? So this is the angle pi over 3. This distance, the distance from the pole, that's our r value. That is 4. Figure it out. What are the x and y coordinates of that point? Of the polar point 4 comma pi over 3. Figure it out. As a hint, it's just a matter of basic trig. It's just a matter of basic trig to get x and y. So x is 4 cosine pi over 3. Y is cosine pi over 3 is a half, so that one's 2. Sine pi over 3 is radical 3 over 2, so this is 2 radical 3. So x and y is 2 comma 2 radical 3. So then for any so this is any generic point here. Any generic point at r comma theta, what do x and y equal? So given the polar coordinates, we're going to write Cartesian coordinates. X equals r sine theta. R cosine theta. Y is r sine theta. It's all based on trig of the triangle that you get when you set up the lengths for the x and y coordinate. That makes a triangle with your terminal side of the angle. And we get these relationships. So now I want you to do this. So, but, yes, these are the relationships, but when you plot a point, r comma theta, there's situations where you want to like still have your brain on and think about it. Look at what you have, and then you can just, you don't have to use these formulas all the time. So keep your brain on. Plot the polar points, study it, think about it, and then decide how you want to find x and y. Okay, so here are your examples. So plot these points first of all in polar coordinates, and then determine rectangular coordinates in the easiest way possible. Brain on activity, not plug and chug, brain off activity. Okay, and then here's the second. We'll get to number 2 on Tuesday. So just do number 1. See if you can plot these 3 points and write them in rectangular coordinates. Just do number 1. Here are the 3 points. A, B, and C. How'd you do? Any questions? That's where the points are. For negative theta means you're going to sweep clockwise from 3 o'clock. Negative r means you're going to go backwards 180 degrees or pi radians from positive theta. All right, what are the coordinates of the point in xy for point A? We just all answer that, right? This is what I was talking about. What is it? You don't use the formulas. You just, it's the point negative 1, 0. The point 1 pi in polar coordinates is negative 1 for x, 0 for y. No formulas needed. Does it make sense? All right, and then the other ones you have these angles, negative 2 pi over 3, 3 pi over 4. You're going to use r cosine theta and r sine theta to get those as x and y. Okay, so it'll be a shorter web work.